Connected, 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 connected. Okay, I'm going to leave it off for a minute. So it should allow you in. So reset the website, reset the... Yeah, it's supposed to say no. So for now, we'll use this.
Okay. So this was supposed to be...
We're doing the question on the screen, not the one that's on your packet. It turns out they're two different questions. Can you show me your work? I want to make sure to see everyone writing it out in your conversions. Please. All right, we have 52 responses. Let's go ahead and talk through this. So first thing, remember we're starting on both sides. What is our starting quantity in unit?
Milliliters in liters.
So in this one we're starting at 45.6 milliliters. We're going to put that over 1. On the other side we're going to say we want to find how many liters there are. What conversion factor do we have to go between milliliters and something, or specifically liters? One liter contains 1,000 milliliters, so we have that conversion factor. Remember that in that box at the bottom of that worksheet, there are about 4 or 5 metric conversions I really need you to have down. And I know that that table does the exact opposite of what I say. I want you to tell me how many of the smaller ones there are in the bigger one. I don't want this to be 0.001 liters is 1 milliliter. That is super confusing. So please say, always a number greater than 1, how many are in one of the big one. So if we do that, 1,000, someone might also write 10 to the third milliliters on the bottom. That would be fine as well. So then we're going to make sure that when we do our calculations, we move the decimal to the right or left 3 places. We move it to the left 3 places, 1, 2, 3, because we're dividing by 1,000. Make sure our units cancel out. Does that number make sense? How do we know it makes sense? What kind of a logic process are we doing here? What logic check? We're always going to logic check this.
Is it smaller than the liters or bigger than milliliters? So you want...
Great, pause for 1 second. So we know that 1,000 of these little guys is equal to 1 liter. Do we have 1,000? No, we have less than 1,000. We have 45. So we know the answer is going to have to be less than 1 liter because 1,000 is 1. We have less than 1,000. That's less than 1. That ratio is always going to hold true. Okay. And then specifically, it's a lot less than 1,000. So it's going to be a significant amount less. We always want to do that because if we accidentally put 1,000 on the top instead of the bottom, we're going to get a really big number and it's not going to make any sense. All right, so let's go ahead and I think the next one actually aligns. Let's see. Oh, by the way, why is the first answer wrong? The whole point of doing these calculations is to find the units, to convert it into another set of units. So I have these as intentionally short answer responses. So it's not just a number is not your answer. It's a certain number of liters for that answer. Okay? Next question. Is this the same as your second one there?
Yes.
Okay, we're converting 65.36 milligrams into micrograms. This is question number 12. Exactly as written on the screen. All right, we have 7 responses. Use U.
Oh crap.
If you're trying to figure out how to put in this symbol, a U is the closest thing I think you have in your arsenal.
Do you want us to read some documentation?
You think that's reasonable?
Do you, I mean, I could just put in the caret.
Sounds good. All right, let's talk through this one, because I think some of the harder part of this is actually entering it on your phone. Is that true? So what are we going to put as our 2 bookends here? Can I get a volunteer? New voice volunteer? Harmon, what do we start with and what do we end with?
You start with 65.36 milligrams.
I'm going to put that over 1.
Honestly, I think I got this wrong, but I'll tell you what I have.
Well, let's not do the calculation yet.
Okay.
We're going to put our units that we're going to try to get to over here. Microgram. Great. All right, and then what conversion factors are we going to use? Do you want to continue going with that, Carmen? Mm-hmm. Okay. Tay, go ahead. 1,000 micrograms over 1 milligram. How'd you come up with that? Did everyone use that? Okay, so don't stress if you didn't do this. There are 2 ways we can do this. So, Tay, can you describe how you decided that was a good conversion factor?
I just know that, and then I Googled it to confirm it. But, yeah.
Okay, it's always good to check logic. Donald?
Because a microgram is 10 to the negative 6, and a milligram is 10 to the negative 3, which is 1,000 off from each other.
True story. So if you look on the scale, there's 1,000-fold difference in size of micro and milli, and the micro is smaller, so there's 1,000 micrograms in 1 milligram. Morgan, do you want to add to that, or had a question?
I was trying to remember what the terminology is that you want us to use. I was just thinking when we're canceling out, we can't cancel it out if the thousands on the bottom to the milligram.
So,
Wrote that out.
I crossed the flag.
so you might be hinting at something that I've heard numerous times from students, and it may or may not be exactly what you're talking about. A lot of people are worried about exactly where the 1,000 is, top or bottom, and it is not important. So in this case, in any case, what's really important is to figure out what the conversion factors are and the right one to use. It's never going to be a concern if the 1,000 is on the top or the bottom. It's making sure that this statement is right, and then that the units are put in a place where they can cancel each other out mathematically. Those are the 2 most important things. So if we did this, we actually come to the appropriate units. How else might we approach this problem? That might take a couple more steps, but that you might feel more comfortable with. Chris?
Converting milligrams to grams.
So how do you do that?
1,000 milligrams is equal to 1 gram, and then 100,000 micrograms is equal to 1 gram.
So I'm going to write those up top here. And so we're going to use scientific notation. So 1 microgram is 1,000,000th of a gram. Or the other way to say that I like better is 1 gram is 1,000,000 micrograms. Million. 10 to the 6th is 1,000,000. So each time we write out what is equal to what, then I want you to write the qualities or the conversion factors that exist. So 10 to the 6 micrograms is 1 gram, and you can write that either of the two ways up there. So now we have 4 conversion factors because of the 2 statements that Chris gave us. He said 1 gram is equal to 1,000 milligrams. So we know that this is a conversion factor to go from milligrams to grams, or from grams to milligrams. Our second conversion factor is 1 gram is equal to 1,000,000 micrograms. So we have 2 conversion factors there as well. So if we do that, we can use Chris's approach. And if we stopped the conversion on the bottom right here, we would end up with how many grams are equal to 65.36 milligrams. But that's not what the question asked. So then we need to convert from grams to micrograms. If we do that, we also see that we converted from milligrams to grams, but grams to micrograms. So we end up with micrograms. Or we can convert directly from milligrams to micrograms. Personally, I would prefer the bottom route, and I prefer, if you're not comfortable, to show the bottom route, because this is actually combining these 2 conversion factors. Questions?
I'm just curious as how it is the bottom. How do you see the bottoms easier when there's more steps? Like the top one seems like it would be the more logical route because there's less steps and less chance to get lost in the process.
So I disagree, because if you're not really comfortable with the metric system, how do you know that this is true? So this is making the assumption you're really comfortable with the metric system. If you are, okay, use it. But if you're not yet comfortable, then, okay, I know exactly how many milligrams are in a gram, and I know how many micrograms in a gram, so that clearly shows those relationships in the bottom approach, and there's no mistaking a mistake there. No introducing an extra mistake there for that reason.
I didn't know that there was 1,000,000 micrograms in a gram.
Yeah, and so I'm asking you to memorize very few things in this class. One of those things is microgram, milligram, or I should say micro, milli, kilo, and centi, I think. The ones that are in gray there, and nano is 10 to the 9th. Nano are in a normal one. Yes? The ones in that table that are light gray and not black, those are the ones that I want you to memorize. Okay? So 2 steps is probably better for this one, if you're not completely comfortable with the metric system yet. By exam time, I will not give you these, and you will need to be able to use these pretty comfortably. Kisa?
How would you math that?
How would I what?
The 10 to the
Oh, how would you do the math?
6, yeah.
So this is 10 to the 3rd. 1,000 is 10 to the 3rd.
Okay.
10 to the 6th. So if we have 10 to the 6th over 10 to the 3rd, what does that cancel out to? 10 to the 3rd on top, nothing on the bottom. So then that means that our value in the end would come out to, there's not really much room here, 65.36 times 10 to the 3rd micrograms, which would be 65,036 micrograms. Is this the best way to write scientific notation? Does that look like a good number?
No.
Why? What's wrong with this if we're writing scientific notation?
You should only have 1 digit.
So scientific notation should only have a digit in the ones place. So on your paper, write down, what is this number in scientific notation? Go ahead and write that down on your own. Check with your neighbor. Nope, not a clicker question. What is that answer in scientific notation? Answer in pink. Mathematically, that's the right number, but scientific notation, that's not appropriate. You only have a number at the ones place and not at the tens. So let's try a number and see if y'all like this. Good, right? Just have a number at the ones place. We don't have any of the tens. We're good. Why? What's wrong?
You're missing the extra exponent.
This is not the same number as this. I made it smaller. This is 65,000. This is 6,000. Nope, can't do that. So what did I do wrong? If I wanted to say it's 65,000, I have to say that it's 65,000. So this number in red in the box is the same as the number in light green. The one in the light green is appropriate with scientific notation. Because scientific notation, if we're reporting a number that way, we don't want to have something at the tens and the ones place. Yes, Jay? So if we write all these numbers out, 65,360 micrograms, right? Both of these are the same number. And the way to write a number in scientific notation is that we put, what is it, the ones, we put something at the ones place, we put a decimal there, and then we say, what power of 10 do we have to multiply this by to get back the original 65,000? So that's 10,000, 10 to the fourth. So scientific notation should only have a number at the ones place, followed by whatever's there. And one thing that's kind of nice about that, how many significant figures do we have here in this number? 1, 2, 3, 4. All these are significant. Before I wrote, that was terrible. If we write this number here, 65,360, how many significant figures are there?
4. It's not dead. Well,
is it 4 or 5? Is it super clear? It's a little bit ambiguous. Technically it's 4. I'd have to have a decimal to make that 0 actually be known as a 0, not a 1. But how many significant figures are there in that green box? 4. It's really clear. There's 4 significant figures. So I really prefer scientific notation because if it's 5 significant digits, I would have included that here. Here, you have to, because you have to say how big it is if you're doing non-scientific notation. So the scientific notation really allows you to say, well, this is how big it is, which is really what that 0 is telling us. And these are the digits that I know are exactly that value. All right. Let's do one more, but we're actually going to do this one quick. We're going to do this in 2 minutes. Question 13. Okay, we're past 2 minutes. Let's talk through how we might do this as 2 steps. Can I get a volunteer? You volunteer? Anyone who hasn't talked yet? You want to volunteer? Go ahead. Okay, and what we're trying to get to in the end is millimeters. Great. Before we do this calculation, do we expect this number to be a really big number of millimeters or a really small number of millimeters? Big. A millimeter is like this. A kilometer is distances you drive in a car. In Europe, they use kilometers instead of miles. So that kind of a distance. So go ahead. Okay, so you combined them. So that's okay. How would we do if we didn't combine the conversion factors? If we went to meters first? Say again? 1,000 what? Over? Sorry? Great. So we know that every kilometer is 1,000 meters, so this way we can convert from kilometers to meters. And then what would you do for the second step of this? Say again? Great. And so you said it was 1,000,000 millimeters over 1 kilometer, which is true. 1,000 times 1,000 is 1,000,000. So basically we're saying that this is 23.05 times 10 to the 6th millimeters. Because we have 10 to the 3rd, 10 to the 3rd. Kilometers cancel, meters cancel. Is that right? Is that our answer?
No. Yes.
Why? That's not appropriate scientific notation. So what would be appropriate scientific notation, Olivia?
2.305 times 10 to the 7th.
Fantastic. In iClicker, you would write 2.305 times 10 caret. There's a little caret 7. We'll probably see it actually if I pull out those responses. There we go. Times 10 to the, that little caret means to the 7. Is there another way to write that? There is, I don't see it up here, but you guys want to know a super shortcut?
Yeah.
Times 10 to the is the same thing as E, and on your calculator it actually is EE. So you see a button on your graphing calculator, other calculator says EE. If you hit that, it's times 10 to the. Super shortcut. So you could have answered this with, I don't know what our number was again, 2.305 E7. That would be how you would answer it with E. Pretty simple and clean, right?
So, I know, like, getting the super big numbers, we're gonna have to do this right, we're gonna go teach it. But, like for this, could we just write out the answer, or do you prefer us to do it?
I want you to practice writing really big and really small numbers in scientific notation. I think it is very valuable because it wastes a lot of time and effort typing in all these zeros. And then if you didn't do it in scientific notation, you would have 23050000, and then you start getting, maybe you're not 100% certain about your sig figs, and you're like, well, those zeros significant, are they not? But here it's really clear these 4 digits are significant, and then any other numbers that you'd have past that are placeholders to tell you how big the number is. Instead of doing that, you just see that it's times 10 to the 7th. You know how big it is, and you know what your numeric value is. Okay, so that was supposed to be 5 minutes of class. How are we doing? We're doing good, right? I'm on the fence about how much time to spend with unit conversion. Can we get a thumb gauge for how we're feeling about unit conversions, at least with the metric system? We feeling confident? Not so much? Or I'm really not so happy?
Thumbs down is like, let's kill it.
Thumbs up is we're feeling okay, right? It's not, yeah, okay. All right, so I see a lot of thumbs up. There was one question that we talked about doing last class that we never did, so maybe we do that, and then I'm going to point you towards a lot of practice, and I'm going to say that there's office hours, there's study groups, there's a lot of other opportunities to engage with this material. I need you to generate questions by struggling and by going through stuff, and then coming and talking about it. The question that we had in the homework due on Sunday that was difficult is I think it said that you dose this many, what was it, this many ounces, and the patient weighs this many pounds.
Yeah, 2 kilograms.
So let's do a blank, and let's write out a question similar, and just see how we might approach that. So, did it give it to you in ounces, or what did it give it to you in? Is this approximately what the problem was? What was different?
We could do this when I was there.
It was something like,
Sorry, I'm trying to listen. There's a question or a statement in the back.
The dosage was in grams. They took 2 aspirins and it was 0.3 grams.
So it wasn't in kilograms?
It was in grams. Thank goodness.
Which I assume
Let's just say 42 grams of the drug. Okay? So I don't have the clickers open right now because I'm blocking that screen. But I want you to try to figure out how we would determine what the dose is using these units. Meaning that if we had someone that weighed a lot less, we would use the dose, milligrams per kilogram, to figure out how much to give them. Try to figure out what this dose is. And maybe I'll spend 2 minutes trying to set it up. We'll come back together, talk about approach, and then I'll let you finish it. Okay, take another 30 seconds to try to figure out how you might approach it, and then we'll talk through an approach. right, let's bring it together. Looking around the room, it seems that it's a bit challenging to set this problem up because it's so different from everything else we've done. When we're trying to find our answer, what kind of units are we going to have our answer in? Is it milligrams? Is it kilograms? What is it?
Milligrams per kilogram.
Milligrams per kilogram. So we're going to have our units, we're going to say milligrams per kilogram. And what is the milligrams and what is the kilograms? It's implied, but it's not stated. What's the milligrams? So drug. What's the kilograms? The body weight, right? And then what are we given to start with? What's on the far left side? Given body weight. And what else? And the mass of the drug. If we know we need it in this relationship over here, I'm going to do the same thing on the far left side. Does this look really different from everything else we've done? We're not starting out with a single number and a single unit. So then the question is, can we get from the unit on the top to the unit on the top over there? Do you know how to convert from grams to milligrams? Do you know how to convert from pounds to kilograms? That might be something you have to look up. Okay, so go ahead and do that and figure out what that numeric value would be. And I realize that 42 grams of any drug is like a horse pill, or 2 or 3 maybe, but, you know.
We're doing an IV.
No, you don't want to do this IV. Maybe suppository?
Oh, no.
So glad I'm not going to be a nurse. Raise your hand if you want another 30 seconds to write out the approach. I'm not as focused on that final number, so make sure you write the approach out, and then if you get a chance to calculate, then do that. Okay, we're going to finish it my way, and then we're going to listen to the easier way that a number of students asked if they could do. So what would the first step be if I want to convert this ratio into that ratio on the right? Can I... Summer? Oh, you were raising your hand for the... Get back to that. Okay. I'd love to hear from different voices. Be brave. Can anyone do it with this approach? Great, go ahead. Great, we're going to convert the grams to milligrams, and how do you do that? Okay, also known as dimensional analysis, 1,000 milligrams are the same as 1 gram, which ends up multiplying it by 1,000, but it focuses on the units as well. Great. So that's going to focus on this component of the drug to milligrams. So if we stopped our calculations right now, what units would we have? Milligrams of drug over pounds of body weight. Great. So what do we do next? We're going to convert the pounds of body weight into kilograms. How do you do that?
I multiplied it by 1,000, but you're supposed to do
So careful, we're converting from imperial or standard units into metric. So what's the conversion factor between... Is that pound, or is that, how many, is, what's...
That's kilograms, because there's 2.204 kilograms in pounds.
Not quite. A kilogram is heavier than a pound, so there's 2.2 pounds in a kilogram. But close. So, the confusing part of this here is that some people then want to take and convert this to kilograms because there's two sets of units. So if we stopped right now, we would have kilograms as our only unit on the bottom, and milligrams of drug on the top.
Why would it be 2.204 and not 2.2?
I just pulled a number that someone said. I don't remember what the exact conversion is from pounds to kilograms. I would look up an exact version and use that. However, if we wanted this to be easier, what would we do? Instead of this whole calculation, what would we do? Separate them. We could separate them. So we could say 42 grams of drug over 1, and we can convert that. 1,000 milligrams is 1 gram, and we could find 0.042, no, other way around, as I messed it up myself, 10 to the 4th grams. And then we could convert body weight into kilograms using that conversion factor. And then in the end, we find the ratio of the two. Both ways, totally fine. Completely accurate. We would not have a difference in outcome.
How do we do it straight across as one equation?
So,
I was trying to set it up, but I couldn't.
like this, you mean?
After
Both
you
of
get set up,
them
how would you
together,
add it?
just one long equation.
That's what he did. This is one long equation. So we would multiply 42 by 1,000 times 2.204. We would divide that by 248 times 1 times 1. And that would give us the ratio of milligrams to kilogram. What numeric value did you find? Anyone confident in their answer? Want to share?
Which one? For the answer?
What is this ratio? I'm going to guess 42,000 over 248. What is that, like 200? What do you got?
I got 373.26 milligrams per kilogram.
Does that sound in the right ballpark? Okay, sig figs, are we okay with that?
There should be 4.
We have 2 sig figs here. We have 3 sig figs here. So which one is going to dictate our final answer? 2 sig figs, our least accurate value, limits how precise we can give our answer. So our final answer is 3.7 times 10 to the second mgs per kg.
How did you get a different answer on the bottom versus what's on top of it?
10 to the third. Right? No, 10 to the second. I'm trying to do math in my head, mental math. Lena?
How is that more accurate?
It is not. So Lena's question is, how is 3.7 times 10 to the second more accurate than 372.26? It's not. That's the whole point. We only know how precise this answer is to two significant figures. This answer has much more precision, and so we don't know this. This is a lie. We only know 370, or 3.7 times 10 to the second. We know it's two significant figures.
So I was following you up into the answer. So when you multiply on the top, it's
like 42,000?
Yeah.
Oh no, it's more than that. Because it's times, yeah.
92, 5, 6, 6.
Yeah.
Then you divide that by 248, and that's how you got the 373?
That's how we should get it. What number did you get?
No, I was just making sure because it looked like you had 373, and there was some supposed to be on the bottom. Okay,
Nope, that's the final number. That's the final value. I was asking what the final number was.
Oh, okay, I'm with you now. So first I was like,
I just asked what was the final value of milligrams per kilogram, and that's what I was told, and it seems like that's a reasonable value.
Yeah.
Okay, so we spent a lot of time doing unit conversion. We're going back and forth, and we're trying to show that it's always about focusing on what is our unit, what conversion factor do we know, how do we make sure that it's aligned appropriately, that it's a proper statement. I need you to be able to do that. There's a lot of practice. So the practice problems are the rest of the climate change packet. Make sure you can work through that on Model 3. There's a lot of stuff with miles per gallon. That's all unit conversion. I want you to set it up as unit conversion. There's on Blackboard under content for week, I don't know if it's week 1 or 2, there's a Miskatoon practice packet. It's like 4 pages of metric conversions you get to practice. So there's a lot of stuff out there. Tony, you got a question?
Okay. So I got the very same answer. I'm like, I did the pounds and kilograms first, but that's okay.
Absolutely. So with something complicated like this, where it is 2 units in 1, I don't mind if you pull it out and do them separately. What I really care about is that you understand how to do dimensional analysis for things where you start out with 1 unit and try to get to another unit.
Okay, I think you misunderstood my question maybe. I didn't do mine separately. I did them together. I'm like, I didn't solve for milligrams and grams first. I did. Do you understand what I'm saying?
You switch these 2, you mean?
Yeah.
That's fine.
Okay.
Yeah. Any order you want. You just have to make sure that you're not converting these grams, or these milligrams now to kilograms, which I saw some people trying to do. That these are really milligrams of the drug, and these ones were body weight. So that's where people can get lost. Quick question, and then we're going to move on.
You said to do the problem set from what?
Under Blackboard content?
Oh,
All right. That was a good start of class. So, not the whole class. I will post the slides with all the work of the rest of the packet, of the climate change packet, so you can go and you can check your work there. There? So today, we're going to be working on unit conversion like we've done, and then we're going to talk about determining the identity of an element and isotope from various different representations. All right? So to start with, we are going to watch a video by one of the quirkiest, most sciencey looking dudes, Linus Pauling. Why is there no audio now?
Oh, I'm so happy.
It literally was just a minute ago. Not cool. Come on, buddy.
It's really quiet.
It's coming out of my computer. Huh, interesting. All right. Always have a backup plan.
Crystals. It was the British scientist Eddington who said that the study of the physical world, and I would say the biological world too, is a search for structure and not a search for substance. If we want to understand the human body, we must know its structure in terms of the cells that make it up. If we want to understand cells, we must know their structure in terms of molecules. If we want to understand molecules, we must know their structure in terms of atoms. And to understand atoms, we must know their structure in terms of electrons and nuclei. One nucleus down in the center of the atom with a number of electrons around. To understand nuclei, as the physicists are trying to do now, we must learn their structure in terms of protons and neutrons, and perhaps mesons too. And it may well be that at some time in the future, the fundamental particles, the electrons, protons, neutrons, mesons, will be found to have structure also in terms of still smaller particles that have not yet been discovered.
Reminds me of Bill Murray and What About Bob?
One of the quirkiest individuals that you would have ever probably met, but he is the only scientist with 2 Nobel Prizes independently to his own name. So very interesting and brilliant, quirky individual. The reason I play this is we're going to be spending a lot of time this semester thinking about the sub-molecular view, but a lot of our interests are in biological systems and how they work. So to me, it's really important that we can connect the two. We're not just talking about atoms for the sake of atoms. We're not talking about molecules for the sake of molecules. We're talking about why is it that things work the way that they do, and how can we predict what's going to happen based off of some of the things we know about atoms that build to form molecules, that build to form organelles inside of cells, inside of organs, inside of bodies. This is kind of an interesting and super creepy soundtrack where it kind of shows us a scale. And so when we're talking about the scale of these things, this is going to be shown in scientific notation. So it shows us here in how many meters, scientific notation at the top and the meters at the bottom. And we're going to kind of zoom in and try to think about where it is that we're going to be focusing in this class. Whoa, wrong way. So each one of these circles is another order of magnitude or smaller.
Oh my god.
So here's millimeters, right? Decimites, LCD pixels. So here's our micrometers. We can now start to see viruses, bacteriophages, and past this point, you can't use light to actually see things. So optical microscope means it uses light. Past this point, there are devices that can measure it, but it's not optical. It's not light-based.
Is it the STM?
SEM? Scanning electron microscopes? Yeah.
I'm looking at this other one. The tunneling one.
There's tunneling as well, yeah. So this is kind of where we meet the interface between biology and chemistry. So biology focuses a lot on DNA, microbiology on phospholipid bilayers, individual components of phospholipid bilayers, the phospholipid themselves. And then we have, even smaller than that, we start to see atoms and parts of molecules. Some atoms that are very, very large. Some that are smaller. This is actually a measurement developed by the Swedes, Ångström, and that is 10 to the negative 10th meters. And that's the size that we talk about for atoms. And we can zoom in even further. And here, it looks, it looks like the nucleus is a pretty big part of the atom, right? But those are not to scale, those red and white particles. Let's zoom in and see how far we'd actually have to zoom in to see those particles. That is how far you have to zoom in order to see those particles at the center of an atom. And then we can go way past that, right? So lengths shorter than this are not confirmed. And we can talk about these weak forces, these particles, these quarks, neutrinos, and it just keeps going and going and going. And all this is theoretical physics. And I don't know if there's anything like down at this level. Is there? Oh, Planck length, quantum foam. Yeah, of course. Sorry. Don't know how I forgot this. So, I want to put that all in context, right? We're focusing on things that are super small. You can't even see with the naked eye, but we have tools that you can measure, and you can actually figure out what's going on at that level. We use a lot of incredible, brilliant people's minds, a lot of physicists, a lot of chemists, in order to get us information about that allows us to make predictions about how things will work, the properties of materials, how people react to drugs, all these kinds of things. So what I want us to do now is we're going to start this activity. POGL, by the way, POGL stands for process-oriented. That's the PO. We're focused on the process, not the answer. It's process-oriented, guided by your team, inquiry learning. So go ahead and start this activity. It requires that you very carefully look at the front page, and then the questions on the second page ask you to go and interpret what's on that first page. So know everything, like look at the stuff on the front page for a minute, start answering the questions, and we'll check in after question 6. If you're not sitting next to someone, please move so you can talk to people about your answers and confirm as you go on. And if you're not clear on any of the questions, flag one of us down.
But then, what is the, that's, are you sure that's 7? Is it act next to 1 or something? Where you go? I thought you had the same amount of Oh, no wonder it's the ions. That's the ion. Look at that. Look at that. What? You see that? Wait a minute.
I didn't see it, but I get what you're saying.
Yeah, so the number of electrons in ions has a negative mixture is different than what you would find in a thing because it's an ion. So it's had one What's your answer?
I got they all have
What's your question? What's your question? Are you right? We're all hydrogen atoms. And ions have, don't they have all one
I don't remember anything else.
Thinking questions, that's what it means. I don't know, something
Means that it's measured because it's more like
Raise your hand if you want another minute to complete up through question 6. Another minute to complete up to question 6. Okay? We'll try to get together in about 1 more minute.
like I'm reading this, and the atomic number signifies the amount of protons in a balanced element.
So, question number 6.
Isn't G just the atomic number? That's the number of
No, that's not That's the weighted atomic number.
That's the atomic number right there.
Something about like
Yes, which is like
That's your atomic number.
What is it? What's it stand for?
And then how many? That's the number of protons.
Bam.
Then we know that that's the same amount of electrons, protons, and ions.
Atomic number is
All right, can I have 3, let's say 2 volunteers? People who haven't talked yet today. Great, and I can't see your name, Ted, I forgot your name. Jocelyn? Okay, and is there a second volunteer? Say again, Rakai? Okay, great. Can you go first? Can you tell us, answer the first 3 questions, which is how many protons are found in carbon-12, carbon-13, and carbon-13 ion?
Okay, so for the first one, you got 6, 6, and 6.
6 protons, 6 protons, and 6 protons. Anyone have a concern with that?
The devil's number.
True. Question number 2. How many neutrons are found in each of those?
6, 7, 7.
6, 7, and 7. All right, so there's a difference there. And then how many electrons are found in each one of those?
6, 6, and 7.
6, 6, and 7. I saw a lot of people trying to figure out what formula to use to figure out electrons. What did this really want you to do? Just to count it, right? They literally were the black dots. So above the images was the key. Black dot is an electron. What is it? Gray is a neutron, and a white is a proton. Okay? So they're trying to get to what is the formula, how do they relate to each other? But that's not coming up yet. So then can I get Jocelyn? Based on the answers to those 3 above, what do all carbon atoms and ions have in common?
Well, the carbon atoms all have 6 protons.
Whoa, slow down. So just about the carbons first. All carbon atoms have 6 protons. And then all hydrogen atoms have? Great. And then the big kicker, question number 6. What is the significance of the atomic number, which we call Z, above each symbol on the periodic table, which you can find around the room? The red number is what it's talking about. What's the significance of that? Great, so 2 things. It identifies the element, and it identifies the element because it is the number of protons. So if I have 5 protons in a nucleus, and only 5, what element would that be? 5 protons. What is that? B, boron. If I have 17, what element is that atom? 17 protons. That is a chlorine atom. Okay? The periodic table is really redundant. Cl doesn't tell me anything more than 17 protons tells me. It is literally any time we find 17 protons inside the nucleus of an atom, that is what we call chlorine. That's hopefully simplifies a lot of that stuff up there. So let's go ahead and work on questions 7, 8, and 9. Basically, keep working ahead. We'll check in probably after question 9.
I have a question. So like with this 13 ion, my question is that is there always one extra electron or can it be multiple extra electrons or if it has 8 electrons, it would have 8 electrons around it.
But then what's happening is this is 6 electrons.
Oh, so what happens if it's an odd number?
What's the charge of the
These are positive. These are negative. Okay.
So if you have two numbers of them,
This is negative. Oh, since it has one extra, since it has that extra,
one extra negative.
one extra negative, then it became negative. So if it was like a 9, it would be negative.
But negative how many?
How would you write that? It was 9.
So if you have 6 positives, 9 negatives, what's the negative? What's the overall?
Oh, the 6 was a 9. Or what am I doing? My brain, somehow it's worded in my brain can't. What's that?
That's where it gets you.
But you'll know that it's negative if you have
a total number of extra electrons.
No, it would have one next to the H means, in terms of like, so because it's an isotope, right? If you see here, this is one H, so a one H plus would mean just no electron. So it'd just be a single. The two signifies that there's a
There was one chapter we were talking about
increase in total would be the number of increasing neutrons. So that's why we're talking
That's what I took. I never had an hour charge. So I was like saying for 8 hours a day, doing it. I never had I regret not taking the 2 semesters just so that I could sink in a little bit more. Something that's so packed. I probably did it all for someone like me, it was very intense.
Yeah.
But it made you feel like, if I can do this, then I can do it.
Oh, for 8? I just said,
All right, let's talk through questions 7 and 8, and then kind of figure out where we go from there. Question 7, what do all nickel atoms have in common? Is it the number of neutrons? The number of electrons? What is it? All nickels have 28? I don't know, I didn't even look at the periodic table. 28. Am I going to ask you to memorize the periodic table this semester? Did I memorize the periodic table? No. I got a PhD in this and I'm not memorizing it, so you don't need to do that. Okay. Question number, you're always going to have as a reference. I'm going to give it to you on every exam. Every time you need it in your life, you're going to be able to look it up. So you need to know how to use that thing and know what all the symbols and numbers and letters mean and the patterns based off of it, but you don't need to memorize. I need you to know how to use stuff and not how to memorize stuff. Okay, question number 8. Why does the notation 13 carbon with a minus sign have a negative sign in the upper right-hand corner? Can I hear from a new voice? Great, Morgan.
There's more electrons than there are protons.
This is one of the fundamental descriptions that is so valuable. A lot of people try to look at, well, it's because it has 7 electrons. It's not. It's because it has, let's see if I can get this to click. If we have 6 protons and we have 7 electrons, these are the shorthand notation for proton and electron. What this tells us is they have the exact, every proton has a positive charge that matches every electron's negative charge. They're just opposite signs. So if we have 6 and 6, we don't have a charge. And then you'll see that as, for instance, carbon 13 would be written like this, with nothing here. But because this one has a negative symbol, what's implied beside this negative? It's a negative 1. Because it has one more negative than it has positives.
So it's based off the electrons and not the...
Neutrons don't have a charge, so they don't play a role in the charge. But the neutrons do play a role in the symbols, and we'll get there in 1 second. So, what expression would we have? What would 8C, does anyone have a good expression? Mathematical expression?
Negative sign? Like minus sign?
Well, it's about how we calculate it. So if we have protons minus electrons equals charge. That works. So if we have 6 minus 7, we get a -1, which is the charge that it ends up. What can be confusing is that electrons are negatively charged. So we have an extra electron in this case, so it's an extra negative charge. Usually negative is like a deficiency, but not in this case. Okay, I'm going to leave you with one slide. The slide summarizes here is a summary that I want you to take away. I know all that technical stuff isn't there, and I'll post this after class. But these are the symbols for a neutron, proton, and electron. How much it weighs in this new mass unit that we're going to be talking about in class on Tuesday or Wednesday, or in grams. Right? We can convert between different masses. But here's the really critical part. The relative mass, or charge, +1, -1 that we just talked about. And that relates over here. What do you notice about the mass of the electron compared to these two? So this is approximately 0 mass. But these two are about equal to each other. So we have mass particles, the neutron and the proton, and then we have charged particles, the proton and the electron. So your homework will have some. I'm going to go back and look to see if we got far enough in class for you to be comfortable completing this. Right now it's due Tuesday night. I'm going to go back and look at that and make sure that that's going to be sufficient where we left off in class. I will send an announcement about the details of your homework. It is not due Sunday no matter what. Tuesday night is when it's currently due, but I worry that we might need a little more time on Wednesday. So I'll send an announcement out about the due date of the homework. Yeah, but they're quick.